Hello and welcome to our Team Deliverable 3. I am Mark Stepanczyk, presenting along with Marcus Masters and Jeffrey Hurd, and we are Team 19 Gearheads. It's a pleasure to be able to present this project to you today. We began this venture by collaborating on some old tech that seemed somewhat outdated that may pose a risk to individuals involved. And what we came up with was that of our cloud seeding initiative. Cloud seeding is a method in which weather modification is altered in order to simulate precipitation. One might ask, why would you want to fabricate or engineer precipitation? And that leads to our problem statement. Increasing weather instability has drastically reduced the water supply and forecasted weather in much of the United States and other regions. This erratic behavior will reduce growing seasons, complicate a variety of commercial services, and intensify wildlife scenarios. Global warming, along with erratic precipitation, poses a threat to agriculture, the environment, biomes, habitats, business, and human existence. The scale of detrimental disaster that this inhabits calls for a current solution to a global dilemma. This leads into our problem context. Our proposed design focuses on addressing a solution where a swarm of drones will be dispatched to a problematic area. A respective sum of calculations will be formed by 3 different robots, utilizing a number of various sensors, gauges, and probes. An end result will be performed by a team swarm communicating with a central hub that results in the immediate and overall increase in precipitation. Our customer base includes a variety of subcategories in the commercial and private sectors, ranging from local farming and agriculture, airports, ski resorts, and a number of various governing agencies, including the military. Our application area is mainly focused in these regions listed. These are the design requirements as followed. Our swarm shall be designated into a cleared, required airspace. It shall be able to identify suitable weather systems in certain environments. The swarm shall be able to compute the necessary calculations in order to execute its mission. The drones shall finally be able to relocate to its designated landing zone. Without further ado, my name is Mark Stepanczyk, and I will be presenting Robot 1 in charge of plasma and crystal dispersion. The first slide rendering the side angle of this CAD drawing features a sleek, aerodynamic, dual-body design of a quadcopter. On the anterior is where the logic is held, and the posterior is composed of the payload. The body composition will be designed using a carbon fiber shell, and the frame will be constructed from a titanium alloy. The next image shows an overhead view where the 4 DC motors are fixed to the frame. Here, the ultrasonic distance sensor is located in the front for a 180-degree range of obstacle locations. A gimbal camera is also located here for userability. The dome on top is a radio antenna for unmanned control of this vehicle. This image exhibits the dimensions. Overall length will be 24 inches, the width will be 12 inches, from ground to body will be 6 inches, and the copter will have an overall wingspan of 18 inches. This photo here depicts the schematics of my drone. Shown in the front is the power source with Arduino, and in the rear is an actuated door along with a pumping mechanism. Here is my circuit design laid out relative to how the drone framework is engineered. UDS in the front alongside a plasma generator. A piezo buzzer is used in conjunction with the UDS for swarm and hub communications. The 4 DC motors spawned along the top and bottom perimeters of the x-axis, and an actuated payload door in the rear. 2 NPN transistors are used to amplify the circuit application. Alongside that are 2 diodes, which will run current continuously one way. I found no need to incorporate a reversing mechanism on these DC motors. Descent can be achieved using a power down, power up initiation. Finally, an LED is placed for air traffic visibility. The actuators are set at 0 degrees, and the system is designed to be fully functional as it lowers on. As my flowchart provides in the next slide, once information is collected from the team swarm and hub, the unit powers on. I will run the simulation. So as my simulation is started, here's the ultrasonic distance sensor in the front. And as a distance is here is affixed, it will let the team swarm and hub know that I will be in range in motion by emitting an electrical pulse in the form of sound. I have my 4 DC motors here on the end. They'll be rotating at approximately 10,000 RPMs. My rear payload actuated door in respect to my quadcopter, and it rotates from 0 to 180 degrees in relation to kind of a pepper grinder. So it will like equally disperse its payload along a certain distance. I have my LED here, which intermittently turns on and off to let air traffic control and other drones and planes know where, so they can visibly see me. Here are the 2 NPN transistors. I have the 2 diodes, which will run the current one way. Just all I need is to go up. I have my plasma generation right here. This will charge the particles released from the payload actuator. Back here. And here's my software design listed. I will not go into much detail about that, but I will provide this at the end of the presentation. Thanks for watching.
Thank you, Mark. My name is Marcus Masters, and I'm presenting the second robot in this group, the Doppler and radar sensing drone. Here's a broad overview of the drone itself. You can see that all electronics are enclosed to be protected from the weather and elements. The dimensions of my drone are 18 inches long by 12 inches wide. The components on the bottom of the drone include the distance sensors, the Arduino board itself, retractable landing legs, and the motors that control the landing legs. The components on the top of the drone include the battery pack, communications boards, GPS board, the Doppler moisture sensor, and the ultrasonic distance sensor radar. Here is the design in Tinkercad once again. And here's the flow chart where the device powers up, receives information from the hub, maneuvers to a location, starts with the radar to detect if anything's in the area. If it fails that, it waits for a second, detects again. If it fails again, it communicates that back to the hub, and then the hub can decide if we need to pick a different area or what's going on. If the radar does not detect any objects, it goes to the moisture sensor. If it has the desired levels, it will communicate to the hub and to the other drones to continue with the operation. Once the operation or objective is complete, the drone is programmed to maneuver back to the hub or home location. Here is my circuit design in Tinkercad. It shows the 4 servo motors which are used to retract the legs on the drone. It includes 2 sensors, one on the bottom, one on the top. The one on the bottom is for the servo motors. The one on the top detects if there is anything in the area. And then I also have a moisture sensor that once it hits certain levels of moisture will send a signal back that the levels are correct to proceed. Here is some of the software coding that we have. Here is my design in Tinkercad. Start the simulation and we'll see that the servo motors are going to start moving. That's the legs retracting. That's based off this distance here. So it's far enough up in the air that the legs are going to retract. This is the top sensor. And once this senses something in the area, it's going to report back to the main hub that an object has been detected. Get close enough. There we go. There's the report back to the main hub. Turn it back off. And then we also have the moisture sensor here. So once the levels of moisture gets up high enough, and it reads that, it's going to make the green light go off, which is the message going back to the hub that the conditions are correct. Up next is Jeffrey Hurd, and he is doing the pressure and temperature robot. Thank you.
All right, thanks, Mark and Marcus, uh, for those great introductions and great slides representing your drones that will be a part of our swarm team. I'm Jeff, part of Team 19 Gearheads, and I'll press on here with cloud seeding based off of Mark and Marcus's great presentation. So I'll just jump right into it. Here's my pressure and temperature sensing robot. There's the initial drawings sketched up and scanned in, and an example of how I hope my Arduino code and would have turned out. So here's my my design. It's basically on the top here. The components are, as you can see here, I got two propellers, one red and green, kind of like lights on a fishing boat at night. So they light up in hours of darkness. I got a couple solar powered rechargeable battery packs. And then I got my two sensors here. One is pressure and one is temperature. And I added some distance sensing lasers. That way we didn't run into anything or other drones while we're in the air there. So the drone is about 12 inches wide, 24 inches wide, and 12 inches deep, and about 6 inches tall. As you can see here from the side, it's got 4 fixed legs for landing and takeoff and recovery. And then on the bottom side, again, like I just spoke about, internally would be the circuit board, power and everything, and running the code, and again, the legs and the main body of it. Just a different angle of the propellers. Here's my electrical design. Went obviously the Arduino board and the battery and the breadboard. I went with a motor for each of the propellers as previously seen, the pressure sensor and the temp sensor. And then there's the attempted distance sensor. There's my software code. Not a whole lot to go into here with this. Very difficult and detailed when you got 4 or 5 sensors. And then here's a basic flow chart for what my individual robot would do as far as power on, manual inputs, GPS coordinates could be input, directions received, drones take off and fly to their operating location, function check in flight again, the pressure and temperature sensors, and then transmit the data back to the hub or to other drones within the swarm. And then once the objective is complete, it'll return to sender there at the hub and hopefully be recovered for reuse in the cloud seeding process. And that's that'll be the temperature and pressure sensing robot. I'm Jeff. Been a pleasure working with everyone. Have a good night.
Our next slide shows our robot collaboration flowchart. The drones receive commands such as location and elevation from the central hub. They then proceed to the location and wait for all the drones to be in place. When the hub gives the command, drones begin to collect data and send it back to the central hub and the other drones. The radar and Doppler moisture drone will first make sure the area is clear of other objects and that moisture levels are appropriate. Once that is cleared, the temperature and sensor drone will detect and report its findings. If all the above situations have been cleared, the cloud seeding solution will be prepared and dispersed. Once the solution has been dispersed, all drones will return to the hub. In summary, climate change and increasing weather instability have devastated the water supply levels, especially in the western United States. The agricultural industry in California alone lost over $1 billion in 2021. Cloud seeding is an innovative approach to help produce rainfall and much needed snowpack in these areas. Our technology is easily scalable, which makes it more cost effective than traditional methods. We can easily add or reduce the number of drones and the amount of solution deployed. This new technology allows 3 different types of drones to work together to detect the best situation for cloud seeding. These drones use numerous sensors and real-time communications to pinpoint the exact location and time to produce more precipitation. When they are finished, they will navigate back to the central hub for charging and for refilling of the cloud forming solution. Once they are charged, they'll be ready to be redeployed. Thank you for watching.